Good morning, everyone. My name is Aravind, and I'll be presenting Memory Augmented Control Networks. This was presented in ICLR 2018 this year. So the previous presentation makes this a lot easier because it's on the same problem domain, and it uses the DNC. So the problem is we have an environment. So basically, it's a planning problem. So we have an environment, and the agent is moving in the environment. Agent collects information about the environment and plans with that collected information about that environment. This is especially problematic in a partially observable environment with sparse rewards. So if in a maze, and the agent can observe only a small square in the maze, and the reward is far away, it doesn't know where to go from that point on. So it has to explore that local position, and then as it moves forward, then it encounters rewards, and then only it learns. So an RNN does work to a point in these problems because it does store history, but in practical cases, we find that it doesn't perform as good as we expect. Hence the need for better models. So a main need that we have in these kind of problems is memory. We need to know, as we explore, what significant information we see and where it is. So the authors in this paper address this issue using two state-of-the-art techniques. So one of them is differential neural computer. Basically, it is a neural network that has an external memory, and it is differentiable, so it can be trained end-to-end in conjunction with other models, such as this planning model. So they combine together this DNC and a planning module that basically uses this planning information, stores that, and then works with that information. So I'll get into more details later on. So the contribution of this paper is that they combine these two networks, and in the planning module, what they do is they do a hierarchical process where they plan in their local environment first, and then use that information to create a global optimal path. So the problem, like I said, it's a maze. This orange square here is the local observable area. So there's a lot of definitions that are in the paper, but the important thing to note is the map, how they represent the map. How they do that is the whole map, whatever is an obstacle is basically -1, and whatever is free to move in is 0. So that is the whole map. And the observable map is obtained by multiplying an observable section of the map. So whatever the agent can observe is deemed is marked as 1, and whatever it cannot observe is 0. So if you multiply the original map with the local field of view, that is the observed location, you'll get this, a subsection of the map that the agent can see. And the agent will only get the previous actions that it took, the previous states it were in, and the goal, which is a point on the map that has a reward, but that goal is only known to the agent when it comes inside the observed view of the agent. So the problem is to basically find a mapping from the observation that we have here. This is the observation, and to an action. So before we go on to the architecture, we need to know two basic concepts. So one is value iteration networks. So the previous maze problem can be modeled into an MDP because we have states, action, and we can make a transition function out of that. And the reward is basically 1 for the state that has the goal point and 0 for the rest of it. And the thing about the reward is the agent will get the reward only when it reaches that goal point. So we can make an MDP out of it. So we can use value iteration if we knew the whole map, right? If you knew the whole MDP. But since it's partially observable, what the architecture does is it uses an approximation of the value iteration. And the main idea is value iteration can be approximated by a CNN using, so this is basically another paper, so I'll explain a bit of it. So what you do here is you take an initial estimate of the value function and stack the reward function, the reward basically for the states on top of it, and you convolute it. So this convolution is basically one iteration of value iteration, and they prove that in the other paper. So if you do that k times, that basically corresponds to k iterations of the value iteration. So the advantage of this is that if you combine it in a neural network, it needs to be differentiable, right? So this is differentiable, and if you combine it with any other models that are neural network based, you can end-to-end train it. So that is why they use this particular value iteration network. So, and they use this to plan in the local observation. Just remember that. Moving on to the next concept is differential neural computer, and the previous presenter explained it a bit, but the difference between the previous one and this one is that the previous one had a 3D model. So, but this one, if you see here, the memory is 2D, and it doesn't have a constraint on where to write it. So it's like an LSTM with an external memory. So think about it as an LSTM that has forget gates, the addition gates, and it's just an LSTM, but it learns to write into this memory. So, and that LSTM is called the controller. And this architecture is based on a previous architecture known as neural Turing machine. So this whole thing is completely differentiable, and the read-write operations are differentiable. Hence, we can combine it in the whole network. If you need more details on this, you can get that from the original paper, but basically you learn the weights for reading and writing through iterations. Okay, so we'll move on to the architecture. So, okay, the first section, if you see here, is the convolution block. So you take the input, that is the map, and stack the reward map on top of it. So what I mean by reward map is the map is a 2D, right? So the reward map will be the same 2D map, but with just the states having the reward, or the goal state will have 1 and the rest of it is 0. And in the problem that is explored here, only one state is a reward state. So you should basically stack it on top and do 2 convolutions and to get the reward layer that I talked about is needed for the value iteration network. And then you convolve it once more to get the initial V. So this will be the output of the con layer. And you pass it on to the middle module called the VI module. So that is basically the VI value iteration network. So value iteration network takes the reward layer and the initial estimate of the value function. Oh, sorry, the other way. Iteration of the value function. And this is basically the first level of planning. So I told it's hierarchical, right? So the first level of planning you do on the local observation. So the current observation that the agent has, and it uses these 2 R and V that we got from the con layer, convolve it again. So according to the new value iteration network, if you convolve these 2 stacked together, you actually get the Q function for all the actions. So, and if you take a max over the channels, you will basically get the value function. So the max over the Q function is basically the value of that particular state. So if you do that once, if you do this step once, you get 1 iteration of value iteration. So you do that k times and get the value map of the current observation. Now we move on to the second step of planning. So we have this value map from the value iteration network. We have a feature representation from the convolution block because we did do a convolution on the initial observation. So we pass these 2 into the DNC. So the DNC with the LSTM take these 2 inputs and learns how to use this information to read and write from the memory. And after reading from the memory, it takes that as well. And with these 3, it gives an output. So yeah, so it gives an output, and the output is basically the action. That is the module here. So comparing this to other work, so the previous presentation, if you saw, it is kind of similar in the sense that instead of using an A3C in the for the planning part, this paper uses a VI, and that's what I think. So comparing this to the paper that I mentioned in the related work in the paper that the authors present, so there are a few other papers that follow this paradigm. So one uses a value iteration network, with a memory, but it's not DNC. And the memory is, and the problem, what they tackle is first-person view, not mapping, movement in a maze. So they basically convert that first-person view into a 2D representation, and they learn the representation. So it's kind of different, but this architecture by this paper does not need to learn to map something to a 2D representation. And another paper by Shen, what they do is they, instead of using a value iteration network, they use a CNN. And CNN plus a DNC, that's what they use. And a very recent paper that the authors mention is neural SLAM. So SLAM is simultaneous localization and mapping. So it is a procedure that is used in robotics to localize the robot in the environment and then plan from that estimate of the localization. That is basically SLAM. So they convert this process into a neural network, and they use DNC for this. And the advantage that they have is that they have really good exploration compared to this paper. That's what the authors also say. So now we move on to the experiments. Now that we have overviewed the architecture. So this architecture of MACN, that is memory augmented network, is compared with first just a base VIN. VIN is value iteration network without any memory. So it just plans with the current observation. That's it. That's what it does. And the second baseline is a CNN plus a DNC. Instead of a VIN, we use a CNN plus a DNC. So the problem with that they always say with the CNN is that it doesn't have history of the past actions or states. But if you think about it, the VIN also doesn't have it, but the CNN plus DNC performs way worse than the MACN architecture. So the third one is MACN with an LSTM. So we have the VIN module, but instead of using a DNC, which is basically an LSTM with an external memory, we use VIN plus and just an LSTM. So it doesn't have an external memory to store long-term planning, long-term significant actions or concepts. In the first experiment, they only compare with the first three, and in the next experiments, they compare also with DQN and E3C. The first experiment is basically a 2D maze that has randomized goal and start positions, and they test with 3 different sizes of the mazes. So they compare these 4 networks, and it's obviously seen that MACN performs much better than CNN plus memory. But a plain LSTM in place of a DCN also performs it well, but not as well as the MACN. So that is a really basic experiment to show that MACN performs better than all the other baselines. So the next idea that they're looking for to prove is that their network can extrapolate into complex mazes. So basically, suppose you have a maze with a local minima. What I mean by local minima is mazes with tunnels. So the current observation, if you go inside a long tunnel, is basically 2 lines, as shown here. So if you just look at this part, just 2 lines. So if you don't have a history of what happened before or what happened like 2 steps before, you don't know. A CNN, basically, compared this to CNN. A CNN sees this image and sees, okay, which way should I go? There's no history there. So that's why the other baselines doesn't perform as well, because it doesn't have store significant events that happen. So what the authors noticed is that the MACN, when it reaches the end of the tunnel, the external memory network changes. So like that was what was shown in the previous presentation. There is this change in the memory network, the external memory, when the observation has the end of the tunnel or when it gets out of the tunnel. But the other baselines have no way of noticing these nuances. That's why we see that CNN plus memory performs at least something, but not as much as MACN, which always sucks. So the problem is a very simple problem. It's just a long tunnel, nothing else. And MACN reaches the end of the tunnel. So till now, they have experimented with problems that are 2D, and action space is just up, down, left, right. So they do one more experiment to prove that their network can scale to bigger problems. So they model a graph, and so each graph has increasing complexity. Like they go up to 36 nodes, and the blue node is the start state, and the red node is the end state. So and the current state is connected to. The current observation is basically only the nodes that are connected to this current state, nothing else. So this is also a partial planning problem. And here also we see that success rate for MACN is huge in the beginning, but it does degrade as the complexity increases. But they note that the degradation is not as much as the other networks, basically. So till now we saw 2D environments, and we want to see how it fares well in continuous control. And the previous ones were just basic up, down, left, right actions. So in continuous control, we have the current position and the orientation of the agent taken into consideration. So the thing about this problem is what they do is they convert this experiment or the environment into their model. So their model requires a 2D. So they basically, so it's a robot with a LiDAR. Basically, it scans its environment. So this is the LiDAR, and it sees the environment. And whatever it sees to the front, it maps into the observation. So basically, they convert the 3D environment to the 2D environment. So, and if you see here, the output that is produced by the network is not the action that it performs, but a waypoint on that map. So, yeah, so and they use that to go to that next waypoint. But MACN performs better than the other one here as well, though. So they do 3 more studies to note how their network performs. So first is how the convergence rate is affected. So they plot that and see that it converges way faster than the other 2 networks that are shown. That is a VIN, plain VIN, and CNN plus memory. And second is that it scales with complexity. So they do an experiment where the goal distance, so the start position is the same for all the models, but the goal is iteratively increased from the agent. So we can see that the performance does degrade, but the degradation is lesser for MACN rather than the other 2 networks. And the other study that they did was, so the previous experiments they conducted with a fixed memory. So for complex environments, we saw that the performance did degrade. So what they wanted to know was, does increasing the memory help? So they took a complex environment, and if you see here, this is the memory size. And as they increase the memory, the performance also increased. So we can show that it does scale when you increase the memory. Okay, so we went through the experiments. And so in conclusion, this paper has a novel architecture that combines 2 state-of-the-art approaches in planning and differential memory. And this actually performs really well. And an observation I had is, like the previous presentation, was that they could have conducted a test with an A3C or a DQN plus a DNC, because they do not do that. They do test the DQN and A3C, but not with memory. So we have a planning module that is a VIN. What if we replace the planning module with a DQN and then add a DNC? We don't know how that fares. Maybe it does perform well, but we don't know. And we also saw, the authors also know that Exploration, oh, sorry, I think my time is up. Yeah, the exploration is can be improved. They do not have any reward, or they do not do anything for exploring in their local space, so that can be improved. That is a future area of investigation. Oh yeah, and the sensors, they assume that it is perfect, and the observation that they have is perfect, but a robot in real life, it has abnormalities in what they're sensing in their current position. They can have errors. So they know that they might also need to learn the sensor model to get a better, accurate, or robust network. So that concludes the presentation. Thank you.